All right, let's dive into a really common problem you'll see in any algorithms class, solving recurrence relations. Specifically, we're going to tackle this one, t of n equals t of n minus 1 plus n. Now, I know it looks like just a bunch of math, but trust me, this is super practical. It's how we figure out the real-world cost of our recursive code. We're going to break it down, make it super visual, and by the end, it'll be crystal clear. Let's do this. So here's the game plan for today. We'll start by figuring out where this relation even comes from. We'll look at some actual code. Then we're going to solve it using two different methods. First, the recursion tree, which is super visual, and then back substitution, which is more of a straight-up algebraic way. After that, we'll nail down the final complexity and wrap up with some tips to help you ace this on your exams. Sound good? Okay, first things first, from code to relation. You might be looking at t of n equals t of n minus 1 plus n and thinking, okay, but where did that come from? And that's a great question. These things aren't just made up for math class. They come directly from analyzing actual, real-world recursive code. So let's look at a classic example.
So take a look at this function here. It's a pretty standard recursive setup. Notice two really important things happening. First, see that for loop? It runs n times, so it's doing a chunk of work that's proportional to the input size n. Second, right after that loop, what does it do? It calls itself. But look closely. It calls itself with n minus 1. It's that 1-2 punch, doing n work and then making a recursive call on a smaller problem. That's the perfect recipe for the recurrence relation we're studying.
Okay, let's turn what we just saw into a mathematical formula. We want to define t of n, right? That's the total time it takes for our function to run with an input of size n. So what does that time consist of? Well, first, there's that recursive call to the function with n minus 1. By definition, the time for that is just t of n minus 1. Easy enough. And what else? Oh yeah, that for loop, it runs n times, so we can just say the work it does is proportional to n, so we add plus n. And that's it. That's our formula. The total time, t of n, is the time for the recursive call, t of n minus 1, plus the work done in the current step, which is n.
So there we have it. This is our formal problem statement. We've got the recurrence relation, t of n equals t of n minus 1 plus n, but we're missing one crucial piece. Every recursion needs a stopping point, right? Otherwise, it just runs forever. That's the base case. For our problem, we'll say t of 0 equals 1. This just means that when the problem size shrinks all the way down to 0, it takes some small, constant amount of time to finish up. So our big mission now is to find what's called a closed-form solution, a simple formula for t of n that doesn't have any t's on the other side.
All right, on to our first method for solving this beast, the recursion tree. I really like this approach, especially when you're first starting out, because it's so visual. Instead of getting bogged down in algebra right away, we're literally going to draw a picture of the recursion. It's a great way to build your intuition and actually see where the work is coming from.
Let's build this tree starting at the very top. Imagine our first call to the function with the input n. What happens? Well, it does n units of work from that loop, right? So let's label this top node with a cost n. Then, what does it do? It makes one recursive call to a smaller problem, the n minus 1 problem. So we'll draw a line down to a new node, which represents t of n minus 1.
Okay, now we're at this second level. We're looking at the call for t of n minus 1. And it's just a smaller version of the same problem. So it's going to do n minus 1 units of work itself, and then it will make its own recursive call to, you guessed it, t of n minus 2. And right there, you can already start to see the pattern forming. The tree is just this long chain, and the work done at each step is just decreasing by 1.
And this just keeps going, right? T of n minus 2 does n minus 2 work and calls t of n minus 3, and on and on and on. It's like a chain reaction that creates this long, skinny tree. And where does it stop? It stops when we finally hit rock bottom, our base case, t of 0. At that very last level, it does its final bit of work, which we can just call 1, and the recursion is done.
So now the big question is, what's the total time? Well, if we've drawn out all the work at every single step, the total is just the sum of all that work. We just have to add up the cost from every level. So we've got n from the top level, plus n minus 1 from the next level, plus n minus 2 from the one after that, all the way down the chain until we get to plus 2 plus 1. Now, this series should look really familiar to you. This is the classic sum of the first n integers. And luckily, there's a super famous formula for it, so we don't have to add it up every time. The sum is just n times n plus 1, all divided by 2. Now, if you multiply that out, you get something like n squared over 2 plus n over 2. When we're talking about big O complexity, all we care about is the fastest growing part as n gets huge. And that, my friends, is the n squared term. So boom, the recursion tree method tells us the complexity is something like n squared.
Okay, so the tree gave us a pretty strong hint that the answer is n squared, but let's prove it for real now with a more formal mathematical technique. This one is called back substitution. It's less about drawing and more about pure algebra, but it's a super powerful tool for getting a rock-solid answer.
So, just like before, we're going to start with our original equation, t of n equals t of n minus 1 plus n. The whole goal of this method is to eliminate that recursive t of n minus 1 part. We're going to do that by repeatedly expanding it or substituting it until we see a pattern.
Okay, let's do our first substitution. We know our main equation works for any input, right? So what's the formula for t of n minus 1? Well, it's just t of n minus 2 plus n minus 1. Simple enough. Now, we take that whole expression and plug it right back into our original equation where t of n minus 1 used to be. And that leaves us with this. T of n equals t of n minus 2 plus n minus 1, all plus the original n.
Okay, stop. This is absolutely the most critical part of this method, and where almost everyone messes up the first time. Your brain is probably screaming at you to simplify, to add that n minus 1 and n together. You have to fight that urge. Do not simplify yet. The whole point here is to let the terms pile up so a pattern can reveal itself. If you start adding things up now, you'll completely lose the pattern. Trust me on this.
So, let's do it one more time, following our rule. We need to replace t of n minus 2. What's that equal to? It's t of n minus 3 plus n minus 2. So we plug that in. Our equation now looks like this. T of n equals t of n minus 3 plus n minus 2 plus n minus 1 plus n. And now, look at that. The pattern is totally obvious now, isn't it? We have a t term with a shrinking number and this beautiful growing sum of integers at the end.
We could keep doing this all day, but we're smarter than that. Let's make a generalization. Let's say we've done this k times. After k substitutions, what's our equation going to look like? Well, the recursive part will be t of n minus k. And the series at the end will be, well, it's going to be a sum starting from n all the way down to n minus k plus 1. This is our general formula that describes the pattern for any number of steps k. So we have this general formula, but how do we solve it? We need to figure out how many steps k it takes to hit the end. And what's the end? It's our base case, t of 0. So we want that t of n minus k term to become t of 0. For that to happen, n minus k has to equal 0. A little bit of algebra tells us that means k must equal n. So we take our general formula and plug in n for k. The t of n minus k becomes t of 0. And that series at the end becomes 1 plus 2 plus 3 all the way up to n. Hey, that's the exact same sum we got from the recursion tree. How cool is that? Okay, so we've hit this problem from two different angles, one visual, one algebraic, and they both led us to the same place. Now it's time to put it all together and state our final answer nice and clear.
Just look at this. It's awesome. The recursion tree method basically gave us the sum of n integers, which we know is about n squared. The back substitution method gave us t of 0, which is just a constant 1, plus that exact same sum. Now you might wonder about that extra 1. But when we're talking about complexity, we're thinking about what happens when n is huge, like a million or a billion. And when n is a billion, adding 1 is, well, it's completely irrelevant. The n squared part is the only thing that matters. The fact that both methods agree is our proof that we're on the right track.
So, the official, formal way to state our result is to say that the time complexity is theta of n squared. We call this quadratic growth. And this isn't just academic jargon, this has real-world consequences. It means that if you double the size of your input, say you go from processing 1,000 items to 2,000 items, the runtime doesn't just double. It goes up by a factor of 4. It quadruples. That's a huge deal, and knowing this helps you predict when an algorithm is going to slow to a crawl on big data.
Okay, let's wrap this up. I want to give you a quick recap and, more importantly, some real strategy for how to use this stuff, when it actually counts, like on an exam or in a technical interview. So you've got two tools in your toolbox. Which one do you pull out? Well, think of the recursion tree as your quick and dirty sketch. It's awesome for getting a feel for the problem and making a really good guess at the answer. It's super intuitive. Back substitution, on the other hand, is your formal proof. It's rigorous, it's mathematical, but it's also really easy to make a tiny algebra mistake. So here's the pro tip. Use the recursion tree to figure out what you think the answer is, and then use back substitution to prove that you're right. It's a killer combo.
All right, if you're cramming for an exam and can only remember a few things, make it these. First, recurrence relations like this come from real code. They're not just random math problems. Second, this specific one, t of n equals t of n minus 1 plus n, always breaks down into the sum of the first n integers. You can bet on it. And because of that, number 3, the final complexity is always going to be theta of n squared. Got it? Good.
And to leave you with a little something to chew on, we just spent all this time solving for t of n equals t of n minus 1 plus n. But what if the work at each step wasn't n? What if it was just a constant amount of work, like 1? So the relation is t of n equals t of n minus 1 plus 1. What happens then? Try drawing the recursion tree for that one. What does the sum look like? I bet you can figure it out using the exact same methods we went over today. Give it a shot. Thanks so much for watching.